Hello everyone, my name is Alvin, and today I would like to show you how to perform fit-for-purpose patient cohort discovery using our interactive classroom tool. Firstly, the ultimate aim of our project is to identify patient cohorts that would most likely benefit from targeted policy interventions. Specifically, we are planning to take advantage of the recent machine learning developments to develop a new interactive classroom approach that is customized for health data to make the result robust and fit for purpose, which can assist in targeted and effective data-driven policy making. One of the major problems that we met when we do the clustering on patient profile is the clustering result is not fit for purpose. I would like to take a very easy example here. Let's say we have 4 people, and we would like to divide them into 2 clusters. We have 3 candidates to perform the task: medical advisor James, policy advisor Lucy, and a K-means clustering algorithm. What will be the result for each candidate? In James' opinion, the clustering should be based on gender. So to him, the correct or fit-for-purpose clustering result should be like this. While in Lucy's opinion, the clustering should be based on age. So to her, the right clustering result should be like this. However, to K-means, the clustering should be only based on distance. Let's compare the K-means result with James and Lucy's result. Of course, they are not the same. So the both health experts may not be satisfied with the computer's clustering result. How can we fix the problem? Well, the answer is metric learning. Let's say we got 7 males and 6 females standing in original space. And if we run a general clustering that is based on distance, the result should be like this. But if we think the biggest difference is gender, then the result is not good, as there are some males and females still mixed up after clustering. Metric learning is called to fix the problem. We first need to provide some feedbacks to metric learning. In this case, we can label some pairs of males or females as similar or different. With the feedback, metric learning will transform the original space into a new space, while similar objects stay closer and different objects stay further away. While in this case, after metric learning, people with same gender do stay closer, and people with different genders do stay further away. And if we run the general distance-based clustering again, we should be able to achieve fit-for-purpose clustering result. So we have applied metric learning to help clustering algorithm automatically learn the purpose, so as to improve the fit-for-purpose level of clustering. But in practice, we have also met some other problems. For example, traditional metric learning requires all the labeling information to be provided in advance, but it is actually very hard or even impossible to figure out what and how much labeling information is appropriate before even running the model. So in our system, we have also applied one of the active learning strategies to increase labeling efficiency. Specifically, we provide visualizations of each iteration of clustering result, which will help to identify the patients who most need to be investigated or labeled. And by paying special attention on these patients, the expert labeling and the whole metric learning efficiency will be largely increased. And unlike the traditional metric learning requiring all the labeling information to be provided in advance, the users in our system can provide their feedbacks iteratively based on the visualization. And they can also stop labeling at any time once they are satisfied with the result. So this technology does make the metric learning even better. This is a whole picture of our proposed interactive clustering system. Now I'd like to expand it by going through all its modules. The first module would be the data input. In our app, after uploading data, user can choose any features to be included or excluded for the clustering. After feature selection, we need to run a general clustering algorithm, for example, K-means, to get an initial clustering result. Our clustering app is quite flexible. Currently, we provide 3 different clustering algorithms. They are K-means, hierarchical, and spectral clustering algorithms. The user can choose which clustering algorithm they want to use and how many clusters they want to have. The system will also provide a function to recommend the best number of clusters that users should choose based on the nature of uploaded dataset. Then the system will do the visualization based on the clustering result. We currently provide 2 types of visualization in our system. They are scattering and hierarchical visualization. In the scattering visualization, each data point is a projection of each patient. Different colors stand for the different cluster labels, all the clustering results produced by the choosing clustering algorithm. And for the purpose of the demo, we specially add the shapes as the ground truth or the user's opinions. In the hierarchical visualization, we can see the result from a different angle, or consider a hierarchy of the clustering result. As we can see from the example here, in the top level, which is level 1, we have 3 clusters, and each level 1 cluster also has some subclusters. Based on the visualizations, the users or experts can investigate any data point and provide feedback in our system. For example, the expert can compare any 2 data points by clicking on the points directly. The user can also investigate an area of points. The system even provides a recommendation function to automatically choose the data points that most need to be investigated, such as the points near the edge of one cluster and also close to a second cluster. On top of this, the users can also utilize the powerful built-in functions for statistical analysis, such as to see the statistical analysis inside each cluster. After all the investigation and analysis and inputting the feedbacks, the user can call machine learning to consume the feedbacks by clicking Update Clustering. As introduced before, machine learning runs behind the scene to transform the original space into a new space, while similar objects stay closer and different objects stay further away. And if we run the general clustering again in the new space, we should be able to achieve a more fit-for-purpose clustering outcome. If the users are still not satisfied with the outcome, they can review the result and do labeling again, and call machine learning again to continue improving the clustering performance. This process will be repeated until the clustering result satisfies the expert. Well, in our example, after several iterations of machine learning, the final clustering outcome is like this. Compared with the initial clustering result, firstly, the current clustering result represented by the colors totally matches the ground truth represented by the shapes. Secondly, in the new space, the similar patients do get closer, while the different patients do get further away. So, I would say, with the interactive machine learning's help, the clustering now becomes fit for purpose. In conclusion, we have presented a cohort discovery tool that is equipped with interactive cluster analysis and machine learning. This system enables users to achieve fit-for-purpose clustering in an interactive, easy, and flexible way. We hope you enjoy the demo. Please feel free to leave your comments or suggestions. Thanks very much.